here's what we are going to do. So I took the liberty of bootstrapping a very simple ink contract. And the way I have done that is just by typing cargo contract new, and I called it coin, which basically gave me this example Flipper implementation. And the reason I've done that beforehand is that when you compile the contract for the first time, it has to install a lot of dependencies. So so I didn't want to have you sit here and watch while the thing is compiling for 10 minutes. So what we are going to do today is basically take this contract written in Solidity. Oh, I think the slash is missing. Which is this contract is taken straight from the introduction to Solidity website. I thought it's gonna serve as a nice example. And given this contract, basically, we're going to learn some Rust, learn some ink by converting this Solidity contract into ink. So if you're new to ink and to smart contracts on substrate chains in general, and specifically on Aleph Zero, ink is not really a separate language, but it's an embedded domain-specific language written on top of Rust, which essentially means it's a subset of Rust with some macros that are contract specific. Then it compiles to WASM, which is what the chain can execute. And to interact with it, you will need, of course, Rust installed on your system. So some Rust compiler, a fairly new one. You will need cargo, which comes with Rust, and which is like a package manager / build tool for Rust. And you will also need, cargo contract, which is basically cargo with some extra capabilities that allow it to, for example, compile the contracts and generate metadata, upload contracts to calls to contracts. So like batteries included solution for contracts written in ink. Now, okay, so without further ado, well, the Solidity contract is pretty simple. It's like a very simple token that, first of all, allows you to send the coins between different addresses, and it will keep the track of the balances of each address in a mapping. And there is this one special address, which is the creator of the contract, which is the minter, that can mint new coins. So like create new tokens out of thin air. And yeah, let's see how we can implement that in ink. Okay, so first of all, this is the Flipper contract that we get just by bootstrapping a new contract with cargo contract. You will notice some attributes here that basically tell the compiler that not to include the standard library, and that the file is non-standard in a way that it doesn't have a main function. Second thing, well, just as in Solidity, you would write contract something. We have the Rust module here. If you're new to Rust, a module is actually very non-magical. So it's just a collection of stuff, right? Under a single namespace. So it's fairly similar to namespaces in C++. In order for the module to actually be a contract, we need this ink contract macro, which will generate a bunch of stuff for us, some convenience stuff, like different types that we can use, and it will check some invariants that need to hold. About that in a second. But yeah, let's get to it. So in Solidity here, you have the contract storage. We can do something similar, right? So we have the Rust struct here, which will be our contract storage, and that is denoted by the ink storage macro on top of it. Now, one of the things that the ink contract macro checks is that a contract has exactly one struct marked with ink storage. Of course, you can have as many structs declared as you want in your contract, but only one can be the actual storage of the contract. The other ones are just there to help your logic a bit and help structure things. So yeah, the struct is public and has some fields inside. Let's go ahead. I'll just delete the comments so that it reads better. So okay, we have the minter, which is cool. Let's have a minter, and the minter will be, well, its address in Solidity. It will be account ID in ink. Maps pretty nicely. In general, you will see that all of the concepts map really nicely. And now for the balances mapping. Now we need to do a small import ink storage mapping. Imports in Rust are also non-magical. They just bring a name into scope. They don't do any code execution like you could be used to from Python, for example. They just bring a name into scope. So now we can just use mapping, and the mapping is a mapping. Well, in Solidity, we have from address to unsigned int. We are gonna write from account ID to balance, which makes sense. Now, one important difference is that the EVM uses 256-bit and unsigned integers to represent pretty much everything. In ink, you have variable storage entries, but 128-bit unsigned integer is the biggest one that's included by default. You can use some libraries to have U256, but yeah, it's a bit cumbersome, but the cases in which you actually need a number of this huge size are pretty rare. So yeah. Okay, so we have the struct here that actually resembles the Solidity one pretty closely. Now, normally I would just go ahead and compile the contract very often so that the compiler can help me in case I made any errors. But for now, I'm still in the process of converting the old Flipper implementation to our new coin implementation. So let's just do a few more tweaks and we will be good to go. Now, since we have a struct, we can also kind of attach implementation to it, right? Just like you would write methods for a class or methods for a struct in C++ or in other like object-oriented languages. What we're gonna do here is, well, first of all, we have the constructor, which is what is going to be called when someone is creating the contract, or instantiating. In Solidity, you have this special like constructor keyword. We don't have the special keyword. The function can be named anything you like, but we need to use this ink constructor macro. And another thing that the macro here on top is checking is that the contract has at least one constructor, right? It makes sense because it needs to know how to initialize the storage and so on. You can of course have other constructors. So I can have new, I can have default, I can have some other constructors with different names and different argument types, initializing perhaps things in a different way. Now, well, new is a good choice for a constructor anyway. Now in Solidity, we have this special global message object. In Rust, we also have a special object, but it's accessed slightly differently. So it would be self, environment, and color is exactly what the msg.sender would do in Solidity. Now, I want to make a disclaimer before I say too much. I am not a Solidity expert. I know it more or less, but yeah, like I know ink way better. So please treat what I'm saying about Solidity with a grain of salt. What I'm saying about ink is hopefully correct all the time. But anyway, please correct me if I'm wrong at any point. Okay, so we can, if you're new to Rust, again, this is how you assign variables in Rust, and this account ID part is actually inferred by the type inferencer here, because this is the type that's returned by the color method. In general, Rust's type system is quite sane and makes a lot of sense and helps you write correct programs and safe programs. So I really encourage you to like get to know it. Okay, since we have the color, well, they are just assigning the minter here. This is actually what we can do as well. We can do this. This is how we would normally initialize a field of a struct, right? Self is basically the struct we are implementing these methods on. So self would be, we could also write coin instead of self, but self is a bit more generic and seems better style. So you'll see that something's missing. And that's because when initializing, you have to be very explicit. So we have another field in the struct called balances, and we are not initializing it. But we can actually do it very easily. So I can write, balances would be, now what's a good initial or default value for a mapping? Well, as you probably can guess, it would be the default method of the mapping. Now, you'll notice that the type inferencer is yet unable to figure out what exactly is this mapping. But once we use it in our struct, it will be able to figure it out. Yeah, the inferencer is actually pretty smart. Now, you will notice another kind of syntax here. Well, normally you write the name of the field, colon, the name of the value you are initializing it to. But if they happen to be the same thing, so I could write this, but since they are the same thing, there's this shorthand syntax that you can just write this, right? And it's pretty convenient. It makes sense. Now I'm not gonna do a default constructor because this is kind of already my default constructor. One kind of interesting thing you can do is actually derive a default implementation of the coin struct, so that the compiler is able to just initialize it to a default like empty value very easily, and then you can change only the specific fields. But maybe let's leave it for now to keep it short and sweet. Okay, we have the constructor. That's pretty cool. We're getting this object created, the struct. Now, another thing that the inc contract macro is checking is that a contract has at least one public method marked inc message, right? So now we can try to replicate the first function from Solidity, the mint one. Okay, I'm going to keep converting what I already have here, because I feel like this is what you would do anyway, right? So start with some template and keep converting it. So the inc message macro, this is basically it's a public method, but it's like a special public method that the users will be able to call from their front end or from the contracts UI, which we are gonna take a look at in a second. We are going to call it mint. And now the way the contracts in inc work, first of all, a message needs to take the first argument that is self. This is not unique to contracts. This is basically how Rust methods work. The self is explicitly passed as the first argument. Because anyway, like the syntax like this, object dot method or dot value is basically a syntactic sugar for just passing the instance of self as a first argument. So it is actually nice and explicit. Now we have the mint method, which in Solidity takes the receiver, which is an address. So I can use our account ID here. And this address is the actual address that an account will have on chain, right? It's not something synthetic and specific to the smart contract. This is like a regular address. Now, the second argument is the amount, which is, well, we're just going to use balance. And balance is actually, but both balance and account ID are type aliases that are kind of auto-generated for us by the inc contract macro. We could actually just stick to a unsigned int here, but I feel like balance is reads slightly nicer and actually reflects the semantics a bit better. Yeah, and in this one we're gonna mimic what Solidity code does quite, pretty exactly. So what it does is first it asserts that the caller of this method is the owner of the contract, is the minter that we are setting in the constructor. So, well, we can use a very similar syntax. We can write assert, and our minter, well, we have this object-oriented setting, so we will have self minter, right? And well, actually the other way around. So self and caller. Okay, and we can I can actually close this. We can say, and well, assert works in a pretty much the same way as in Solidity. We can optionally pass a message here, so like only a minter is allowed to mint. That's kind of obvious, but well. So what this will do, if this equality here doesn't hold, is it will basically abort the execution of this call, and yeah, just kind of panic essentially. We are going to see that there's a much better way of handling failure in the contracts, but to kind of showcase the equivalencies, we can use this one. And now what happens here is that they basically the syntax that is used here, in my opinion, is very implicit. A lot of things are happening at once and a lot of assumptions are made. So, for example, there is an assumption, as far as I understand it, that if the receiver key is not present in the mapping, it will be 0. So we can just add this amount and it will work. We have to be slightly more explicit, but it's all good since I think it results in slightly more readable code. That's for every developer to judge for themselves, but I like what's going to happen here in inc. Now, first of all, we're gonna check how can we, yeah, so we can call it receiver balance because we are gonna add some tokens to the receiver's balance. So I would like to know what the balance was beforehand. And the way we're gonna do it is actually pretty clever. So we're gonna just take the balances field, issue a get function. Well, since the mapping is from an account ID to balance, then when I issue get and supply an account ID, I should get balance back. And that's true. That's partially true. So I'm not getting balance per se. I'm getting optional balance, right? Because a certain address might not be in the mapping yet that I'm trying to mint the tokens to, as will often be the case. So the option that's returned is basically a type like this. So it's option that can either be some, well, it's actually option of some value, and it can be, yeah, sorry, that's basically it will look like, sorry, it will look like this, right? So it can either be a box containing the value or basically nothing. So this is what's returned by this method. And we don't have to do any ifs or pattern matching and so on, because, well, the reasonable value to return if the account is not present in the mapping is to return 0, or in other words, the default value for this mapping. So this is precisely what this unwrap or default method does. It will either extract this value that was already there from a box, from the sum box, or return, well, 0 is a default for pretty much any number type. So now this works really well in the context of what we are trying to do. And since we want to now add the amount here to this balance, we're gonna do a very simple thing. So we're going to say self balances insert. Okay, here is insert. And now one quirk here is that basically well, I would write receiver here, and these prompts are distracting me really. But okay, so, and receiver balance plus the amount, right? This works, but this needs to be a reference, and it should work. It's just what the signature of this method imposes. I'm not going to dive into the specifics of references and borrowing and so on. If you have been to my other workshops, it was covered pretty extensively, and I'm sure it will be in the future again. I'm trying to keep this one more practical and more focused. So yeah, this should work. Now we're gonna do one more thing, because what's happening here in Solidity when we mark the address as public, the minter as public, is it effectively auto-generates a getter for the minter. This is not what happens in ink. So we will have to actually let's move this method and move it above, because I somehow like to have the getters above. This will be a message that we will call minter, because why not? And it will be returning an account ID, and it will just return self minter, right? Notice that there's no ambiguity here, because a minter method is a completely different beast to a minter field / address, right? So this will work very, very nice. And notice that in ink, when the message doesn't modify storage, it will be just marked as a &self. If it does modify storage, like we do here, for example, by inserting two balances, it will need to be marked as mutable self reference, basically, which is cool, because, you know, if you at any point inadvertently try to mutate something you didn't intend to, the type signatures will probably let you know, the compiler will let you know. Okay, now it seems that we have replaced just enough of the template contract to actually be able to compile this. Let's do just this. Cargo contract build with the release option, so that it's, you know, nice and optimized and everything. And now it compiled very quickly, because it was already compiled in the previous version. So all the dependencies were fetched and compiled and so on. You'll notice that it's essentially doing two things: building the code itself and then generating metadata, right? Because when we have a contract like that, we have, well, first and foremost, the actual WASM binary, the blob, and we have the metadata. And the metadata is actually, sorry. If we inspect the metadata, it's basically, it's the ABI, right? It's telling any external parties where are the methods in the binary, how to call them, what are the arguments, and also what are the docs, which I'm going to talk about in a second. If we inspect the WASM, it's not much to look at. I think I don't remember the command, but you can definitely decompile this WASM into like a Lisp-like assembly and view what's happening there. But it's actually pretty hard to understand what's happening in the WASM. But I think you rarely need to. And the contract here is basically, well, just actually it's described here, so I don't know why I'm saying this, but it's a bundle of the metadata and the WASM blob. It's just more convenient to work this way, because you have only one file to handle. Okay, so it compiles. That's great, but we haven't implemented all of the functionality yet. So okay, we have the mint. Now we have the send function, which is slightly more involved. Oh, and you may notice that I'm not writing any documentation. I I can, if I write 3 slashes like this is basically a doc string, and I can include some documentation in line, which is definitely recommended or even necessary, because this is what's going to end up in the metadata, and it's going to be very helpful for the users of your contract to basically know what's going on inside of your contract. But without further ado, we can now implement the send function, which is, well, it's slightly more involved, but still, the logic is fairly simple, right? It just subtracts the amount from the sender and adds it to the receiver's balance. That's, yeah, pretty self-explanatory. But it also needs to be it also needs to mutate the storage. Now the params will be the same roughly as minting. Well, minting is a special case of sending. Actually, it's kind of like transfer without the sender, right? The tokens just appear from thin air. So anyway, we have the signature that roughly resembles what we have in Solidity. Now, you will notice that in Solidity here we declare an error, insufficient balance, and this is also what we would do in Ink. And you will need to excuse some of the boiler. Oh, sorry. My enter key gets stuck sometimes because I work so much. Now I'm going to try and type this out. I do have it written down because, okay, so essentially we want to create an enum, which is, if you know enums from other languages, it's very similar. If you know algebraic data types from like functional languages, it's also similar. It's a very nice concept, basically a type that can be one of the variants. And we are going to call it, let's call it coin error, right? Because why not? Now, we are going to pretty much have only one variant in this scenario because, just to keep it short, but in general, here we would create a variant for each and every error condition that might happen and that we might want to report. Now, we are going to call it insufficient balance, just as our Solidity example to the right. Sorry, different syntax. And the syntax is essentially the same now for the variant as with the struct. Let's see. This is the balance requested, which is going to be a balance, and balance available, which is also going to be a balance. Oh, you'll notice that I'm leaving trailing commas, which is what you are able to do in Rust in general, and kind of makes it convenient for you because I can now just copy this and already have the comma. Yeah, if I do it like this, I unfortunately will get an error while compiling. Or maybe not. Oh, I don't, because I haven't used it yet. But anyway, I would get an error. Let's actually see this. We are going to handle errors in a way that we will return this result type. At the risk of being obvious here, the result is similar to the option type we got from the get function, with the difference that result can either be an OK, so to type it out, the result will look something like that, right? So a result is either an OK with some value inside, or an error with some error type inside, right? And it can be either this or this, right? Let's delete it for now. Now, we need to specify, of course, what is the type of the OK value, and inside the OK value, and what's the error type. So the OK value is basically empty parentheses, which is like nothing, like a void type, unit type. And for the error, of course, we have our coin error that we can return. That's great. Now, well, it's highlighting this because we declared that we are returning some result and we are not. if we omit the return type at the end of the function, it kind of assumes that the function is returning this. So the nothing type, the unit type. Now, we will need to check the condition similarly to what our Solidity counterpart is doing. So, okay, if amount is greater than balances, and we need to get from the balances, and we will get from the color of this message, right? This is the sender, the from here. So this would be self and color. And we're going to do unwrap or default, right? And some logic further down the line. Now, we are getting slightly redundant. So instead of writing this again, I will introduce a small helper. Inc message. It's going to be a useful message anyway, right? So I'm going to write balance of. Don't need to mutate anything. And let's call it who of any account. And it's going to return balance. It's always going to return a balance, 0 if someone is not in our mapping. And we are basically going to be lazy and reuse what we already have here. Only the name is slightly different. This should work, right? This always works. It's like guaranteed by the type system to always return something. Now the cool thing is that we can replace this and say balance of receiver, which is worth noting that just because something is marked as a message doesn't mean you cannot use it in your code and reuse it, which is pretty cool. So now we are going to do the same thing with one more thing. We are gonna get the color again, just to make it, or actually let's call it from, because it's from and to, this is the sender. We could call it sender or like her. So we can use balance of from, right? It makes sense. If the amount we were trying to send is more than the balance of the sender, we can easily return. Return works just in other languages, except that it is not necessary if this is the last line of the method, right? I need to be a bit quicker because I'm going over time slowly. Okay, we just want to return the error variant here with our coin error, insufficient balance. Now, the requested amount is the amount here. Let's format it nicely. Requested is like this. Available. Sorry for being slightly chaotic. From balance is balance of from. If this is more, we are available is basically what the balance was before. Do my parentheses match? Yes. Just so that we can get rid of the errors. What's the problem here? I'm sorry. Yes, and now we got to the error that I was kind of hinting at. If we compile this, we're gonna get an error. Something about unsatisfied trade bounds and so on. So, well, turns out that if you want to return something from the, if you want to return something like the error, it needs to have some more stuff implemented. And we are going to do that. So we're going to derive a few things. Now I'm typing. And please don't worry too much if this all looks scary. It's pretty much a no-brainer because every time you implement an error, you will basically paste something like this. And yeah. Config attribute now. And we have this. yeah, looks pretty scary, but basically this derive, it's what's telling the compiler to kind of figure out an implementation of a certain trait on its own using some default rules and so on. And these traits basically allow the whole system to figure out how to encode certain types so that they can be stored on the blockchain, returned to the UI, and so on, right? Oh, this warning here, just because, okay. Now seems like our errors are gone, but our method is not yet ready. What will need to happen is, and this is actually an important part, right? If you remember the DAO hack, the order of the lines that come here is actually important. So first of all, when we are doing the transfer, we are going to subtract from the balance of the sender, right? So from, if you remember how we've done this, is from balance minus amount, right? This is subtracting from our sender's balance, right? So from the caller's balance. Now, if we do to balance will be the balance of the account we are sending to, and it's a self balance of receiver. Should work pretty nicely. Yes, it does. And we are going to do a similar thing. I would like to warn you against copy pasting because it's very easy to make a mistake like that, but I'm trying to save time. And the plus here, right? The logic seems to track, and we will return just an empty OK to let the system know that they'll know that everything is OK. Let's try compiling this. Yay, it worked. So we have only one thing missing, right? You see the event declaration here. The purpose of the events is exactly the same, and actually the semantics also in Solidity and in Ink. We will, well, as you probably are able to guess by now, we are going to create a struct called, well, it's called send here. Create a struct, mark it with Ink event, and we're gonna try to have the same fields. So from will be an account ID. To will be an account ID, and amount will be a balance. So what you can do additionally in Ink is, well, since the events are intended to be ingested by some external analyzers, you can kind of tell them to index a certain field of the event, kind of like the database index, right? By writing Ink topic, but let's skip that for now. Okay, we have the event. Now we can, once we've done all of the processing here, we can say self and emit event, and now we need to create the event, right? So the event is called send, if I'm not mistaken. Send or send? Oh, send. Okay. And we have from, well, to will be the receiver, and amount. I think that kind of works. Let's see. It does work. That's great. So I think we have more or less arrived at an implementation that's equivalent to what we have in Solidity. You can see that it's a slightly different philosophy when it comes to writing code and what needs to be implicit or explicit, but basically maps one-to-one almost. Now, and arguably is very type safe in the way we write it here in Ink. To the left. Now, since we have compiled this code, let's very quickly try to deploy it. Oh, I already did deploy something. So I can say upload new contract code, and we're gonna call it coin. Let's see. I want to, yeah, that's my coin contract. It's checking whether the bundle is correct, so on and so on, analyzing the metadata. Seems okay. And now comes a very important piece of information. you can see that this is called upload and instantiate. So the difference with what you might be used to from EVM chains is that the process of uploading and instantiating a contract is actually two different things. So first of all, you are uploading the code to the chain, and well, code or the bundle, the WASM bundle, and then from the bundle uploaded on the chain, you can actually create many instances, and which means it's very cheap to kind of upload the code just once and then create multiple instances, right? It's way cheaper than uploading the code again every time. And this is actually, this problem, for example, is what I believe the EIP 1155, right? That the multi-token is trying to address. In Ink, you can just upload, if you want to create 100 PSP22 tokens, you can just upload the code once and then create multiple instances, right? Okay, but back to this instantiation, we have a constructor here, only one, so there's not much to choose from. There's a few things here. Basically, there's the limit for the execution time and limit for the storage that it's gonna take. Now, you don't have to like estimate it yourself. The system is doing a dry run and seeing, well, dry run, which is like running it, but without uploading to the chain, without actually changing anything on the chain, right? So it knows how much gas this is going to consume. So that's cool. We can deploy it. Okay, we have a contract deployed. So we can, yeah. You will notice that the calls that do not modify the chain return immediately, don't require signing an actual transaction. If we want to mint, we can mint from Alice to, let's say, Bob. I'm using the substrate contracts node to have a testing environment. So I have some development accounts with some funds, and I can say that I'm minting 1,000 coins to Bob. Dry run says that it will be successful. That's very cool. We can do the change. Now, if we tried, for example, transferring from Alice to Bob, and Alice hasn't minted anything to herself, from Alice to Bob, you will see that the contract will revert with the error we declared. Insufficient balance, requested, well, some amount. It's basically the 100 we requested with the 12 added decimal points, right? Available is 0. Makes sense. If we do the same, try to transfer from Bob to Alice, it will be successful, right? Because Bob has enough, because we just minted to him. Okay, and that's basically about it. Now, the last cool thing, because before we move on to the Q&A session, would be we have this pretty cool product that's slowly finalizing its development. It's called Smart Beaver, and yeah, I think it's, in terms of, like beginning to write contracts, if you come from EVM world and are used to the Open Zeppelin wizard, this is kind of trying to do the similar thing. So I can do stuff like the token name and symbol and so on, and it will generate the you will see that it generates the code, and yeah, it's pretty much a ready-to-use implementation. I can select some extensions and so on. Yeah, I just thought it's a cool thing to share. It's going to support more token types soon. Yeah, so that would be about it.